And Bayesian inference also from
Yeah, Bayesian influence. Yes, we also already talked a little bit Bayesian, right? I guess that's the core of the Bayesian influence where we talk about. So it's like the concept is extremely simple. Right? The difference between Bayesian and map is maximum estimate, a posterior estimator is really like Bayesian. You take into kind of like average of all the estimate, right? So you don't just take the maximum, the highest probable, and use that as an estimation, but you take all the possible and average out. That is the Bayesian, basically. But then like knowing that afterward, then you just need to look at, okay, what kind of distribution you can deal with, because if you just everything just have like px or py and so on, you cannot do much with that. Like every time you just a discrete distribution that have a totally arbitrary kind of like um, PDF, then you cannot do much other. For example, you cannot even deal with like continuous random variables, right? So to deal with like continuous signal, then the simplest one would be first look at Gaussian. That's why, yeah, as I mentioned, why we will spend quite a bit of time on Gaussian. And so we talk about coherence matrix just now, like and also of course PCA, yeah, and also PCA, and then next we'll go back to Gaussian, and then we just look at several property for this multivariate Gaussian. So now we know that the Gaussian just kind of defined. We're looking at the multivariate Gaussian defined by the mean and also the coherence matrix. So and let's say if I can. So C here is like basically n by 1, I say n by 1. So maybe let's say if I can split the random variable into multiple parts, let's say I have x and y here. C split into x and y.
only two variable.
No, more than that. Like this vector as well. Let's say x can be n by 1, let's say, and y can be like n minus n by 1, let's say. Yeah. And then now we have questions. For example, like how do you marginalize this x? For example, like this is the PDF like PCC will be something like whatever this way, this guy exponential something like C minus mu C. Let me write better.
Only n by 1.
Why it should be n by 1? This is a random variable, multivariate random variable.
Multivariate
Yeah.
Random variable. It means that not only n by 1 but n by n, because that's multivariate. So n by n.
No, I'm talking about the variable. You're talking about the coherence matrix or what?
No, I mean that because that's multivariate, so it means that will be n by m or n by d, n by q, because we have in here also n by n or n by q, so this one also should be n by q.
No. This should be n by n.
Yeah, n by n.
This is n by 1.
Yeah, therefore this one will be n by n also. No, because this is n by n.
No. I'm talking about you're pulling a random variable. The random variable itself is n by 1.
N by 1.
The variable itself is n by 1. It's a vector random variable.
Yeah.
Yes.
N by 1.
The mean will be n by 1, right?
Yes, that's right.
The coherence will be n by n, right? Because the coherence is computing like for each pair. Each pair, like what's the basically like the coherence, the ij element is this one, right? something like that, right? So it's a square matrix, like n by n square matrix, right?
Oh
Yeah.
yeah, that's right. Square. N by n. Yeah, that's right.
So again, like maybe I write it better now. The PDF. Let's just remind you guys the PDF for this is something like determine 2 pi sigma. Maybe I'll put sigma c here. Exponential minus 1/2 c minus mu sigma inverse c minus mu, right? Something I have a transpose here. Oh, okay. Why I put an integral? I don't have the integral here yet. So that's the PDF, right? Now I can play with this distribution in multiple ways. For example, I can ask you, what's the marginal distribution? What's the marginal distribution? For example, like what is p x? So we say I kind of like ignore this y part now. I just want to look at the x. So I know the entire thing is a Gaussian. What's this first m part, for m components? What is that distribute? What's the distribution of this first m component?
M component?
Yeah.
Gaussian?
Yeah, it's also Gaussian.
Yeah.
But why?
Yeah, because central limit theorem.
No. That has nothing to do with central limit theorem. Yeah.
That's because part of that.
We will show that this is actually tedious, but we will show that. Yeah, this is actually Gaussian as well, but it's not obvious why it's so. It's a tedious algebra for that. Or we can ask, for example, like conditional distribution. What's the conditional distribution? So for example, like what is px? X given y is equal to some small y. What will that like?
Yeah, that means that.
For example, we have this original distribution now, but instead, like okay, here in the first question, this first question here is we ignore this component here. We just look at how it's distributed for the first m component.
Yeah.
That would be the marginal. I mean, the second case would be okay. How about if I observe for the last m minus m components? Let's say I observe that as a small y. What will be the new distribution now? Yeah, for x, the remaining m components.
Yeah.
So yeah.
It can be calculated.
Yeah, that can be calculated, and that can be kind of yeah, that we will calculate it now. Actually, it's a little bit tedious, but we will calculate it now.
Yeah, that's pxx. This will be pxy.
You mean px? You mean this one? Oh yeah, okay, yeah, px given y, yeah.
Yeah.
Yeah, let's write this.
And then I mean that this one times this one, that will be pxy. That's right.
No, it's you just want to times py y, right? Something like that. Yeah.
Py y. Yeah.
That we multiply that will be like.
Yeah. That will be like. That will be.
That will be like pxy. Yes, that will be pxy. I know this pxy here is like maybe I should write it this way. Xy is actually Gaussian here. Yeah, I know this one is Gaussian.
Yeah.
And we already like kind of jump forward by saying that this will be Gaussian, also the marginal one. And let's go one at a time. Like let's just show this. This may already spend some time, like a little bit time for that. But we will go through this exercise anyway. So how to compute the marginal distribution here?
Marginal distribution, what? This one?
This one, yeah.
This is, we already have this one, and then just divide by p y.
No. That is not. I'm saying the first question here.
Oh.
What's the marginal distribution here?
Marginal distribution there. So this We don't have any information.
You have information is only this one, right?
Oh, that's
And then
why.
like you have C is basically is like X, Y, something like that.
Oh, okay.
Right?
C is X, Y.
And this is a these are vectors also. Like be careful.
And you want to know the probability of this one?
Yeah, probably of this one. Yeah.
Oh, yeah, we know this one also.
We know the probability of this one is like this PDF, right? It's given by this guy. Yeah.
And this one we already know. No?
Why?
Yeah, why? We don't know.
We don't know. Yeah, we don't know.
So
We know the entire thing, but we don't know like X and Y.
Oh,
If we know Y, then it's symmetric, right?
yeah.
It's the same as knowing X.
Yeah. Yeah. So it's just inference from C. We can derive from C.
Yes, yes.
We can derive from C.
Okay, so what should we do exactly?
Just by some Bayesian.
This is something to do with Bayesian. So what's PXX?
PXX.
Given that PCC is this guy.
Oh, that's that's Markov.
Has nothing to do with Markov as well.
So that should be same. That should be same. Hold on. This minus.
Before going into the algebra, what is this exactly? Like just high level, like what is this? Like you're supposed to marginalize the distribution, right? How do you marginalize the distribution?
How do you marginalize distribution?
Yeah.
But I need that about the Bayesian.
No, that's have nothing to do with Bayesian.
How to marginalize? How to marginalize that? We should ask the actually X is something like from Z. Marginalized from Z.
Yes, from C, right? This is from C here.
Yeah.
Of XY, like C is actually XY, like. Right, then what next? Then
Oh yeah, we already have this one. X,
you have
Y,
this here.
and divide. Divide.
No, derive.
Is divide? No.
No,
We cannot
we are
divide.
not computing condition. First question again, you're looking into more or less the second question. The first question first, how to marginalize, like, you marginalize if you remember some of this example, like for example, like ring and whatever, like you have like true and false, or like we gave like example, for example, like let me go back to, let's say like sunny, what's the weather, like sunny and rainy, and whether like the fall is wet or not wet or something like that. We put in some probability, let's say just arbitrary put something not doesn't make sense, right? Let's say like that, right? So we say like marginalize would be okay. I just care about, instead of like probability, let's say this is like weather, okay, weather variable. This is like for a variable weather. Instead of like looking at like both variable like for and weather, we just want to look at like maybe just the weather equal to S or something like probability of weather. Then to marginalize will be like what? Summing over all the probability that when it's sunny, right?
Yeah,
Let's say
that's right.
that would be like equal to like P W.
Oh yeah, this one should be summing to Y.
Yes, this is integrating all to Y, right?
Yeah.
Okay. So we can start from here.
Yeah.
We can start from here. So then will be algebra. That is like kind of tedious algebra, but we'll go through that anyway. So we have PC is this guy here. Then let me erase this now. I don't need this anymore.
But with that we have information of Y because we summing into Y.
Yes, we are summing over Y, but you look at the expression, it's ugly.
But
It's not that easy.
But we have Y here.
Yeah, we have Y here, but yeah, we have Y here.
We have information of Y.
Yes, but as you can see, like it's kind of more tedious than you think, right? If you just look at this thing here,
Okay.
this piece here, So 2 pi, let's write sigma instead of sigma c, like just make it more easier. So and I have basically integrate over this thing. So I have exponential 1/2. Now let me write it as like x minus mu x, like y minus mu y transpose sigma inverse x minus mu x y minus mu y dy. Right? Is that something like that, right? So it's basically something like, but it's kind of like ugly. So lots of like tiny algebra here. So here I'll just say shorthand notation because it would be like too painful. So let's say I say define x tilde is equal to x minus mu x, y tilde is equal to y minus mu y. And then let's say I have like sigma is equal to split into sigma xx. Can I write it easier? Like sigma xy, sigma yx, sigma yy. I write it this way. And by the way, like because sigma is symmetric, yeah.
Why that would be x y x y y?
Okay, this is m by n.
Yes.
This is m by m.
M by
M by m.
M by M.
This is m minus m by m minus m. And this is accordingly. This will be like m times m by minus m. This is m minus m by m. Yeah. So so note that like it's kind of symmetric. So therefore, like you have like sigma xy. I think it's like sigma xy transpose equal to sigma yx or something like that.
Oh yeah, I see.
Yeah.
But that is not xx. This would be xy to yx. This is yx.
Yeah, this is why it's like it's why it's just my handwriting. Like this is why it's here.
Yx, that's why.
Yeah.
Yeah. Then it could be like that.
Yes.
Yes.
And sigma is kind of because I have to do an inverse here, it's kind of complicated. So let me define sigma inverse as some other matrix called lambda. And by the way, there's a name for lambda. This is a precision matrix.
Precision matrix.
Yeah.
That's lambda. That's sigma.
Yeah, it's like just sigma inverse. So the kind of intuition is like sigma is the variance, right? The bigger the variance is like more uncertain, right? And the inverse would be like how precise your random variable, right? So if like its precision matrix is larger, and then of course when you say a matrix is larger, it's kind of vague. What I mean is like the eigenvalues is larger, then roughly speaking, like your variable will be more certain. So it will be less uncertainty.
So it means that there is precision metric? No, there is only precision matrix. Precision metric and there.
Yeah. Precision matrix is just defined as a sigma inverse.
And this will be, if precision metric is more small, so it means that will be more precise.
Sigma, yeah, no, precision is big, then will be more precise.
More precise.
Yes. Precision big, then like your variance will be small actually. Yeah. Because I inverse, yeah.
And then when the variance small, it means that the lambda will be.
Lambda is very small as well. If you are the lambda, mean the eigenvalues of the will be small as well. Yeah. And let me write also the precision matrix as a lambda xx, lambda yx. So basically, I'll partition the matrix similar to like what I did to this guy here.
Yeah.
Lambda yy. So I write this way, then like this I can actually expand this way. So expand this. I will have this guy here, and maybe I just ignore this basically, and then the rest will be, I have minus 1/2 x minus mu x transpose lambda xx x minus mu x minus 1/2, let's see, y minus mu y transpose lambda yx x minus mu x minus 1/2, what's that, x minus mu x transpose lambda xy mu, sorry.
So you calculate all of them, all of the component of 4 of them. Yes. Yeah, calculate that.
Not precisely. You need to do computing square stuff like that.
Yeah. So you basically times this one to that one, this one to that one.
Yes.
And then this one to this one, x mu x. Yeah.
So if you look at this guy, you have dy here, y are variables, right? Have these are variables y. This one is actually does not depend on y, so it's actually a constant. I can actually put it out in terms of y.
What is that?
It's actually a constant with respect to y.
Yeah. What
So
is that? This one above.
Yeah, this one, right?
Okay.
So I can pull out that guy there.
Yeah.
So I only have the remaining 3 left.
3 left.
Yeah.
There is y in there. And then you should integrate that.
Yes, and I should integrate that. Is kind of painful actually. Let's see. This I put it out, but let's focus on these 3 guys here. These 3 guys, as I mentioned, I just shorthand this notation as. Let me put 1/2 out. 1/2 minus 1/2 out. This is I use y tilde instead. Y tilde is instead of mu y minus y minus mu y. And y tilde lambda yx x tilde plus x tilde transpose lambda xy y what?
This still plus.
This is tilde, yeah, plus y tilde transpose lambda y
Yeah.
y tilde. Yes. Okay, so far so good. So what?
Integrate.
Yes, integrate. That's of course there's exponential here, dy here. Then you have mainly you have some bunch of constant outside. And then for this guy, okay, what should we do next?
Integrate.
Yes, but how do we integrate that?
Yeah, that's easy. Simple. Just for that, e is minus in there, and this one 1 by 1, and this one.
No, you cannot. All these are matrix.
Yeah, this matrix. Sorry. Yeah, this matrix. Yeah, just.
Yeah, these are all matrix, so you cannot. Yeah. So
Yeah.
you need to be very careful. This is I forgot the size here, but anyway, all these are matrices.
Yeah, that's matrix.
So what we need to do is do a computing square trick.
Yeah.
So we want to make something like similar to the original Gaussian distribution format. So we want to switch into something. As you can see at this, I have like lambda y here. Most likely I can change it to something y tilde minus something, y tilde minus something, transpose. I can transform into that, right?
From where that's there?
I mean this. Oh, okay. I'm just giving you a high level sketch yet. So we're going, but we want to from here hopefully become something like this. Then this will be like more or less a Gaussian transform. Then if a Gaussian, you know how to integrate that because it's a Gaussian distribution. You integrate that will just give you the mean. No, not exactly. Give you equal to 1 basically.
Yeah, that's right.
So then let's try to computing square make it look like this. So then you can see this. I can make it as what? Let's start with lambda yy at the middle. If I have y tilde, let's see. or let's look at this side. Y tilde. Of course, I have this. Then I will cover this term here, right? Then now think about, for example, this term here. I have Y tilde here. If I have plus lambda y x tilde.
This one from where?
No, I mean if I put a term like this, this multiplied by this guy, I will get this term, right?
Okay,
I put a transpose here.
oh yeah, that's one, and this one.
No, I'm actually, I can, if I have this one here, it turns out everything is great. This guy transpose, I will get this.
Got that.
I mean this guy transpose times this, I will get this. You see, is that correct? Oh, okay, wait a second. Okay, I made a mistake. I'm sorry. I made a mistake. Let's go back. Let's see. It's almost correct. So I have y tilde here. I have transpose here. Y tilde transpose. I have a lambda y here. I need to put a lambda y inverse first, right? Lambda y inverse m times lambda y x. And then x tilde, this guy multiplied by this guy multiplied by this guy, I get this term.
Oh, okay. But
Right.
when does yt from here go and here? So you find this.
Yes.
Yeah, because you multiply with this one first.
Yeah.
And multiply with this one.
Yeah.
And this one.
This one. By the way, this multiplied by this will give me this term, right?
Oh yeah.
Yeah.
Yeah, because this one is this one, and this one, and this one. Yes, that's right.
So I'm saying that if I repeat this, the same thing here. This multiplied by this will give me this term.
This one will be there, and this one d.
So I have this one. The inverse will be the transpose will be x transpose x tilde transpose, right? And then I have like lambda y x transpose and lambda y inverse transpose times lambda y inverse times times y times y tilde. Then okay, I missed this. I have this multiply lambda y. This guy, this is basically the transpose of this guy times lambda y times y tilde.
But this is minus. This is inverse.
Inverse.
Okay.
Yeah, but okay. Inverse and transpose, but remember lambda y is symmetric.
Yeah.
So therefore lambda y inverse is actually symmetric as well.
Yeah.
So therefore like this is the same as a lambda y inverse. So this will got cancelled, right? And lambda y x transpose is just equal to lambda xy, right? Because I lambda y.
But we know that if inverse in here, because we are in the positive definite, so it is same with this one.
You mean like why the transpose? Why the matrix is symmetric or what?
Oh, because this is actually metric. Yeah. So metric.
It's symmetric, right?
I mean that this is also metric. So
yes.
So it means that we have inverse matrix of this one. We have that.
Inverse of this is inverse symmetric, but inverse and transpose, but the matrix is symmetric.
Yeah.
So therefore, like the inverse and transpose is just equal to the inverse, right? Just equal. This is just equal to lambda y inverse.
Yeah.
And lambda y inverse times lambda y is just equal to, and then that is gone.
Lambda y inverse is not similar with lambda y. No. It's not.
No. It's not unitary. It's just symmetric. You have this coherence matrix and the precision matrix are symmetric. Yeah.
So we have inverse then, and then we got it.
So then they cancel. Then this is actually equal to this term, right? So 1 multiplier is equal to this term. This multiplied by this multiplied by this is equal to this term.
This one cancel.
This does not cancel, but this will become like lambda xy, right? Lambda y x transpose is basically lambda xy.
Yeah.
So therefore, like this is x tilde transpose lambda xy y x tilde. So it's actually this term here.
Yeah.
So that's great. So we have a competing square. This multiplied by this by this, I have this multiplied this by this, I have this, and this, I have this one. So I have one more term left, right? I have this term, right? So I need to subtract this back. Subtract by x tilde transpose lambda xy.
Why should we subtract?
Oh, because I have additional term, I am computing square. Okay. I only have 3 terms here. Here expanded, I should have 4 terms, right? I have 4 terms, right? I have 4 terms if I expand this expression here. I need to subtract back the last term, right? Because the last term is not in here.
In the last one, maybe you can scroll down there. Scroll.
I mean this one, like this multiplied by this, multiplied by this, is not in here, right?
Oh yeah, it's not in there.
Yeah, so we need to subtract that back.
Oh yeah.
Yeah, so x tilde transpose lambda xy, lambda y inverse, lambda y multiplied by lambda y inverse, lambda y x tilde. We need to subtract back this guy. It's kind of ugly. This one is can I simplify it a little bit? Only this is erased. It's basically x tilde lambda xy lambda y inverse lambda y x tilde, something like that.
Yeah, that's right.
But this part is okay. This part, basically, we know this is just a Gaussian distribution, right? This is a PDF of Gaussian distribution. Yeah. If we integrate that, what happened? We need to be careful. This is not exactly equal to the Gaussian distribution because the Gaussian distribution have a normalization term, right? Have a normalization determinant 2 pi lambda, right? Or 2 pi the variance of this guy here.
Yeah.
So the variance in this case should be like lambda y inverse, right? Because the
variance there.
Yeah.
Yeah.
Yes. So therefore, like, if I integrate this part, let's just get back this. So therefore, if I integrate this part, it should give me square root 2 pi determinant lambda y. Determinant 2 pi.
Q function.
No, it's not a Q function. It's not Q function.
No.
It's not Q function. We're integrating the entire thing. Yeah.
Okay.
So, I mean, originally, if you have a PDF like this, PDF like this, let me look at this one for example. I have a PDF like this. If I integrate this whole thing, what is that? It's just equal to 1, right? Now I integrate this part and ignore this part, right? Then I integrate this part, I should give me like square root determinant 2 pi, the coherence rate. Just that. So therefore, as I mentioned, I integrate this part should give me square root determinant 2 pi. What's that?
Integrating that will be square determinant.
Yeah, this part. Lambda y inverse. Yeah. Because the coherence now is like lambda y inverse.
And then because that's because 1, and then therefore that should be that. Because
yes, because this is equal to 1, right?
Yeah, so just the constant is that integral.
Yes. I mean, integrating this thing is equal to 1, right? And so now I just integrate this thing, then it's equal to this guy, right?
Yeah.
Yes. So now we can summarize everything now. So the integral, the whole thing, eventually will become something like this.
So you no need to integral that one.
We don't need to integrate now, as I mentioned.
So you already have that.
Yeah, we already after the computing square. I have this one. It looks like a Gaussian distribution, right? But I'm missing a kind of like normalization factor. By integrating that, this will be just equal to the inverse of that normalization factor, right? And that inverse.
But we have that. We have that. The last
That is a different normalization factor. You mean this one?
I mean, no. This one. Out. This one. We should integrate in this one also.
Yes, but this is not a. This is a constant. It does not depend on y.
There is no y.
There's no y. Check. There's no y. This is all x here.
This y.
No. Y as a variable, like this is the coherence matrix and the precision matrix are constant, right?
Oh yeah. That's
They're constant.
yeah.
Only y are variables here.
Oh, okay.
Yeah.
That's fine.
So this you can pull it out. So like let me summarize everything. So this one, as you said, I should pull it out. There should be something like minus exponential minus x tilde transpose lambda x y.
But the first
what?
first thing it should be there, but that could be go there, and then you integrate that. So this is become go there. So this is and this is the time, yeah, and then this is the result of integration of this one is this one times this one.
Yeah. Yes. I haven't finished that. That's what I'm saying. Like, so let's pull back this guy. Lambda x y was wait a sec.
Inverse.
I have lambda y by inverse first. Actually, I think I'm not. Yeah, I have lambda y by inverse here. Lambda. Let me just try to write better. Lambda y x tilde. Yeah, I have this term. And from here, I have this term here, right? So I need to multiply. Let me erase something here.
But this one should be positive then.
What?
This should be positive.
No, there's a negative sign here.
But this one
Oh yeah, you're right.
positive.
Yeah, let's see.
Yeah, because
I have a minus, maybe it's positive. Let's see.
Yeah, because you go.
Yeah, you're right. Let me correct this. There's a 1/2. It's actually I'm missing 1/2 also because I have 1/2 here.
Yeah.
It's a 1/2 this guy. Yes, you're right. Thank you. So and also I have this term here,
Yeah, that's right.
and I have one more term because originally there's a normalization factor. I omit this here. So I also have the original normalization factor is this guy here.
Yeah. Normalization factor.
Yeah. Because we copy here and then we ignore that, like we didn't look.
Oh.
So we need to copy it back. So it's so I think I have everything. Wait a sec. I think I still miss something.
Yeah. Normalization.
Oh, okay. I also forget this thing, right? When we expand this guy, this term we already at the beginning we say this is a constant with respect to y. Yeah, so we also need this term, so we always have a term minus 1/2. What is that? X tilde lambda x tilde, something like that. Yeah. Okay, that's everything.
But I think this one normalization it should be because that will be there. So that's it should be same in here. Because this will be go up in here because this is at below before, and integration of this one is this one. So this one should be go up. That's why
I don't understand.
this one should be in here.
No, 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 no. Here, there's two different things here.
Yeah, that it's
No,
mean
no,
that
no.
this
Wait, wait, wait.
is-
Let me repeat. Like start from the
yeah,
beginning, maybe, or like
to make more systematic. So because
you have
to-
start from here, right? Let me use another color, maybe.
yeah, make
You
it
start from here, like integrating, right?
Mhm.
Let's repeat everything. Like this, I can write it as the PDF is like this, right?
That's right.
Then I integrate like this guy, and this is a constant. I just put it away. I put it here. I didn't do it. I didn't touch it. That's why it should be still the same thing here, right?
Okay.
And then like okay, look at this. Another guys I expand that. Like then I have like they expand like this. And then the first term here is a constant, right?
Mhm.
If then I put it out as well, right?
Mhm.
Then I only have like these three terms left.
Mhm.
Then I did a computing square, right? So computing square, this can be
Mhm.
divide is like put this one half back maybe. So it's equal to this multiplied by this and then like minus this guy, right?
Equal to 1.
Now I and then like
Integral.
then I integrate this, right?
Yeah, that's equal to 1.
This is constant. I put it out again. Like it become this term here, yeah.
Mhm.
Only like this one I integrate this guy. This guy is equal to this one, right? Because if I integrate this, this is equal to 1, right?
Oh yeah, yeah.
And then this put on the other side, therefore integrate this guy is equal to this one, right?
Yeah.
So
Pull up there.
now I have everything, right? Now everything should be
But,
going on.
This should be minus.
This is in because I remember the Gaussian format here. Like the coherence matrix, the PDF here should be like inverse of the coherence matrix.
Mhm.
So therefore it should be inverse.
Oh yeah, yeah, that's right.
Yes.
Mhm. That's right. Okay. And then
Yeah.
this one you find from this guys, this term, and this one you find from where is it? Oh, from there, from there.
Yeah, yeah, yeah,
scatter.
yeah.
Yeah, from here.
Yes. Yes. Yes.
Okay.
Okay, yeah, it is tedious, but we almost there. We have so we at least we bypassed the integral. We didn't need to do the integral, so that's the great thing. So then that's the rest. Now what next? Let's see. This one I can group some terms here. This become exponential minus x tilde transpose sigma xx. Let's see.
You want to grouping that? You want to combine that? E exponential.
Yeah, minus lambda xy, lambda yy inverse, lambda yx x tilde, right?
Yes.
Yes. Okay. This just okay. Simple. To just group them together. But then like these terms here, I argue that this is actually just sigma xx inverse. So why is so? Because let's see. Let's say I have this look ugly, but let's consider just I have a matrix like A B C D. So this is a square matrix. I just split into A B C D. So you can think of like A B C D here is a is a sigma xx, sigma yx, sigma xy, and so on. And then like let's say if I have the inverse is equal to A tilde B tilde C tilde D tilde, let's say. Then so then let's look at what's A inverse. A inverse is equal to okay, let's look at A times A tilde minus B tilde D tilde inverse C tilde. I think I have a transpose here somewhere. Does it? Maybe it does not. Yeah, I think it's right. So I try to look at this guy because I'm claiming this is the inverse of this guy here. I'm claiming this will be the inverse of this one here. So therefore, this multiplied this, I'm expecting this will be equal to identity. So let's just verify that.
But, why you have this one?
Hmm?
Why you have this time this one? What from here?
No. Again, what I'm saying that like I'm claiming that like the inverse of this guy is equal to this. I'm claiming this will be A inverse. So therefore, I just want to verify whether this multiplied this is indeed identity.
And why you from where this you get it? From where this?
No,
this
I'm
is
just trying to prove it.
just to prove that.
Prove like A inverse is equal to A tilde minus B tilde D tilde inverse C tilde. Yeah, I'm trying to prove this.
Okay.
So, okay, I guess it's better I write the whole thing. So if this, then this, then I'm trying to prove that, prove this guy. So let's try A times this. I'm expecting this is equal to identity. So let's see. So this is equal to A tilde minus AB. AB tilde D inverse tilde C tilde.
Yeah, you want to get that.
Now, but let's look at like, because the inverse of this A B C D is equal to A tilde B tilde C tilde D tilde. So that means that like if I look at the off diagonal, I have A times B tilde times B times D tilde should be equal to 0, right? What I mean is like A times B tilde plus B times D tilde equal to 0. Right?
Yeah, hold on. This one, this one, this. Why?
From here, like if the inverse of this matrix is equal to this guy here, then this means that this means that A B C D multiplied by A tilde B tilde C tilde D tilde is identity, right?
Yeah, identity.
So it should be like that, right?
Yeah, that's right.
So therefore, like A times B tilde plus B times D tilde should be 0, right?
Yeah, that's right.
So I have this one here, right?
Yeah.
So therefore, like A times B tilde is equal to minus B times D tilde, right?
Yeah.
So therefore, this would be A tilde plus B times D tilde inverse C tilde. So now it's equal to A times A tilde plus B times C tilde.
Yeah.
Yeah. But
Hold on.
yeah.
Because this one, D. Where is this? You substitute this one.
Yeah. Substitute A B tilde now is equal to minus B D tilde, right?
B tilde.
Yeah,
minus,
sure.
So that is
Yeah.
positive then.
Yeah.
And then this one will be same. So B
So
is
it was
C.
yeah. So but then like if you look at this again, like A times A tilde times B times C tilde should be just equal to identity, right?
Yeah.
So therefore it's just equal to identity.
Yeah. So that's right.
Yeah, so therefore like this is actually inverse of this guy, right?
Mm.
So therefore we can use that like now what's ABCD here is like let's see.
That's right.
Yes, that's right?
This is A.
Yeah.
This is B.
Yeah.
This is C.
Yeah. Therefore like you have that, right? So okay, maybe I erase all this now. So if you agree that so this kind of simplify a whole lot because then this is actually just equal to sigma y, right? Sigma what? Sigma xx, yeah.
Yeah.
Sigma xx inverse, right? This is just equal to sigma xx inverse. Actually, this is all we already have done, right? Because you see, like that means that there's the. Actually, honestly, I don't even need to check this guy because this is a constant. We know that this is the PDF, but let's check it anyway, right? If you look at this guy here,
This one should be sigma xx, not sigma lambda xx.
hmm?
In here, lambda xx. No,
Sigma what?
sigma lambda xx.
What lambda xx?
Because you prove that this one, and this one should be this one a, this one. So actually this one.
Therefore, like this is the A inverse, right? This is
Yeah.
equal to A inverse.
Yeah. So what is A inverse in here?
If A is sigma xx, right?
A
So
inverse.
A
A inverse in there. What is?
So this guy here is a sigma xx, sigma xy, sigma yx, sigma yy, right?
Yeah.
This other side here is a basically lambda xx,
Mm.
lambda xy, lambda yx, lambda yy. So therefore, my sigma xx inverse is equal to sigma
A.
xx, right? Sigma xx
Yeah.
minus b
Yeah.
tilde is a sigma xy, right?
Yeah.
Yeah.
Basically, A is sigma xx inverse. Yeah. A sigma xx.
Yeah.
Yeah. This one is sigma xx. So therefore, A inverse. So.
Yeah. So this is sigma xx inverse, right?
Okay, that's fine.
So, okay, I really can erase part of it now. So, now what I'm saying, like actually here I can claim is I'm already done,
Yeah.
because in terms of it's already a form of Gaussian distribution,
Yeah.
because and also the variance is I sigma xx, and what's the mean is actually is like x tilde again is equal to x minus mu x, right, as we explained earlier on.
Yeah.
So therefore x is actually really a Gaussian of mean mu x and like variance sigma xx. But whether I should
But the result is actually already like that.
hmm?
The result of the result is this one times this one, and this is will be this, and this is x t and x t. So that is the result.
Yes, actually, therefore we expect this part is actually should be the normalization factor for this Gaussian, so should be something like determinant 2 pi sigma xx actually. You can verify that this actually is equal to determinant 2 pi sigma xx.
Oh, okay.
Yeah.
Yeah, it's the same one with the way you proved that before.
It's actually it's not the same, yeah, but
It's not the same.
I'm not sure I should go for that. I can actually I prepare that. Let's see. Okay, maybe I will go for that anyway because let's see.
Yeah. We believe that.
Mm.
Yeah, with some way we can do that.
Yeah. Maybe I just give a comment like how you actually do it. It's like
Maybe something like this. I think just using like something like this.
no,
No? And can we get that?
no, you cannot
Because
actually.
this is why.
You have a determinant where it's different.
Oh yeah, this one is
You have a determinant
That's
here.
more difficult, I think. No, I don't know. That is because
Actually, this is not but it's not that. Yeah, therefore actually it's more tricky than this part. Like here you can directly verify. This one you need to know something to do it.
Yeah.
So for this part actually, like if you want to verify that, basically like you know that your sigma. Maybe I start with a new page here.
So you want to prove that?
Maybe a little bit, like maybe not the entire thing.
Okay.
Let's say like you have sigma. I would just like make it shorthand. Like I say the sigma is like A B C D instead of like sigma xx sigma xy, just easier to write. So if I take a determinant of sigma, so the idea is like trying to decompose these guys, and know that there's a fact for determinant. It's like determinant A B is equal to the determinant A. Let's see. No, actually, determinant A B. Yeah. Is equal to determinant A times determinant B.
Yeah.
So then what you can do is try to do decomposition for this guy. So
We first decomposition that one first.
Yeah. So that's like do the elementary decomposition. Something like I have this row elimination and so on. So for example, like I can for this guy, I can just uh, write this as like I zero D times A B D inverse C times I. So you see, like what I do is I decompose this guy into two matrices. Basically, in the second matrix is this is a kind of like useful decomposition. Like when you have matrix, you think of this as a kind of a column vector. This basically, I'm saying that for the first element of the vector, I'm not doing anything. In the second element of the vector, I multiply by d, right? So then so therefore like this is equal to this. And then I can further decompose this guy into something like I try to kind of like add this into this one so that I get this part into 0.
Yeah.
So if I do that, like, then I basically you can show this is equal to this is eventually equal to I B 0 I times A minus B D inverse C 0 D inverse C.
So you decompose the second one become 3.
Yeah, I decompose the second one into this.
Okay.
So, but then like once you do that, then you compute determinant will be very nice, right? Because this one, the determinant is actually just identity, just equal to 1, right? Because like this is 0, they say, yeah.
Oh, yeah.
And this is actually just determinant D. Yeah. And this is just determinant, this is I here. A minus B D inverse C. Yeah.
Yeah.
And then like we used the earlier results that this is actually equal to A tilde inverse. Something like
this one A minus B C. Yeah, only this one.
yeah.
Yeah. Okay.
Yeah.
This
Yeah.
one. And
Then like we used result earlier, we have like sigma equal to this, if like sigma inverse is equal to A tilde, B tilde, C tilde, D tilde, then like A tilde inverse will be equal to like this guy here. So therefore this is A tilde inverse. So therefore like we have like determinant of sigma is equal to determinant of D times determinant A tilde inverse. Or like this will be equal to, therefore like determinant sigma is equal to determinant sigma yy. D is determinant take sigma yy times determinant A tilde is like lambda xx inverse, I think. So then I think that will give us the result, basic harmonics. Yeah.
so that's simple, more simple.
Yeah, it's not simple actually. It's just I jump very quickly. So but
that is come from there because we already know this one. X is one, this A there, and then this one D is, so actually D this is sigma yy. This is sigma yy, sigma xx, sigma xy, and sigma xy.
that's an xy, yeah.
And sigma yx, and then we have this one, so go to here,
Yeah.
and for this one come here, so we have that,
Yes.
and then next
Then we're done actually. Maybe I put a 2 pi here.
yeah,
It's the same with a 2 pi here.
2 pi.
Yeah.
Because we have 2 pi,
Yeah, because we have 2 pi, it's better to put 2 pi here. And
so,
and more, of course you can somehow I prove this expression, but by symmetry like this will work also, like 2 pi sigma xx times determinant 2 pi lambda yy inverse, the same thing. I mean you can show this is also equal to this, and then if we go back like what we have here in the equation, if sigma is that way, then this is therefore equal to for the determinant 2 pi lambda y inverse and
That is why.
yes, that's why I try to cancel it because and 2 pi sigma xx, right?
Yeah. And that would be cancelled.
So therefore this can be cancelled and then only have this left behind.
Yes, that's right.
Yes.
And then we find that.
So just yeah, but actually as I mentioned, like even you have this part because you know this is supposed to be a PDF, you can also confirm that like this must be true. Actually, even though yeah.
So we have this one as constant and not constant, and this one as minus in here, and this one. Well, actually, this one you want to put in here. This is why you want to put in there. So you want to prove that this is Gaussian. Yeah, this is Gaussian next to it. X.
Oh yes, the final is like this, right?
Because this is a Gaussian, therefore X has all.
Oh no, actually, remember that's what we did at the beginning. We just use this as a shorthand notation. Shorthand notation. This x tilde is really equal to x minus mu x. It's just I write it. I think I put it here. Yeah.
Oh, yeah.
Yeah, I
That's
put it
right.
here. Yeah.
So why you want to exchange again to x in there? You want to change? So?
No. Here at the beginning, like we don't want to keep writing this way. So, but really we are interested in the original x way.
Oh, okay.
So we put it back, but then you look at the format. That what you have is really just the format. Therefore, is like something like that way.
Yes. Okay.
Determinant 2 pi sigma xx exponential minus 1/2 x minus mu x sigma xx inverse sigma mu x, right?
Oh yeah, that's right.
So and this is exactly the Gaussian PDF for like mean with mu x coherence matrix like with like sigma xx, right?
Yeah, that's right. That can be also become sigma yy. Sigma y.
If you are marginalized
Yeah.
x, yeah.
Okay,
I mean, if you marginalize x and just consider y, then yeah. So
So that is the result.
that's the result for
Integration.
we say the first question here. So as I said, like it's intuitively it's obvious, but it's actually pretty tedious to show that. So it's if you marginalize the distribution, meaning that like if you have the entire distribution is John Gaussian, multivariate Gaussian. If you only look at part of the variables, that part is still like Gaussian. Yeah. Now then, let's look at like how about conditional. If I try to condition.
Even m is really short.
Well,
It is still normal because you only take one part of m and then you just get m length. So it is actually this is actually m length m because you get actually for the first one is you have n
yes,
and you just get x as m.
yes.
So this is short,
Yes.
short. But how it really short? Maybe only two. It's still normal.
Yeah. Of course, I still have that form, right?
Yeah.
Like the proof is general, right? It doesn't use any assumption.
There is
After you do that's I guess the critical part is that you try to bypass the integration, right? The real trick here is doing the computing square. Then you know that okay, you look at that form, you know this is a Gaussian PDF. Therefore, you know what is supposed to be the integration. So you
that is not limited by
No.
how long how length.
no,
short
there's no assumption here. We didn't impose any assumption here.
Okay.
Yeah.
Okay.
So again, let's look at the second question here.
Yeah. Conjunction.
So if I observe something like y, right? Then what is the px given y here? Then as you said, okay, actually this part is more like you mentioned, okay, this will be kind of like base rule, right, in this case. My px given y x y equal to y, in this case is really like p xy, right? Xy over p y, right?
What is it?
Yeah.
What is this?
Px given y.
Px given y.
X, y is equal to y, or maybe then it's like px xy,
xy.
and this py y, yeah.
Py y. This is a Bayesian.
Yeah, this is a base rule.
Okay.
Yeah, so, and now we already did the first part, we know like what is py y now. This is still like Gaussian, and should have the covariance matrix like sigma y,
Yeah.
and mean like mu y. So then let's, this part is actually a bit easier because we know we did the harder algebra.
Yeah.
So then like p x given y, that part is kind of, so just consider the exponent now. Let's ignore the normalization factor. So it will be something like 1/2. Let's see. Again, let me just write x tilde is equal to x minus mu x, and y tilde is like y minus mu y. So just make it easier. So then I say x tilde y tilde transpose sigma inverse x tilde y tilde, and minus y tilde sigma y inverse y tilde, right? The exponent is just that, right? This is exponent coming from pxy, right? This is coming from py.
Oh yeah.
Yeah.
That's right. Pxy. Py.
Yes.
Yeah, that's right.
So
So that's already done for that.
no, it's not done. We want to know exactly what is this, right? Or we write down the algebra, we want to know what is this, right?
For Pxy already done. I mean that this is for this one. You want to see this one, and this is Pxy, and this is Py. So
No, it's
so when you want the calculation, first of all, we want to find what the Pxy. What you want?
it's not done because this is not a Gaussian form. You look at this is not exactly a Gaussian form here. It looks like it's not. If it's a Gaussian, it would be like x tilde transpose times some sigma xx or sigma something times x, right? Now I have something else tagging along here. It's not something Gaussian.
Yeah.
Just look at this shape, it's not. So we are not done here. So let's try to expand this again. Like let's define a sigma inverse again as lambda. So then we have like this again, like lambda xx, lambda. I mean, let's okay. This will be lambda xx, lambda xy, lambda y is lambda xx, yx, and so on. Then expand this guy. I have like sigma tilde t lambda xx x tilde plus, okay, let's put 1/2, something like lambda xy x tilde y tilde lambda yx y tilde x tilde, and I still have y. Right? I have something like that. I have a one term here also, like y tilde sigma y inverse y tilde. Right?
Show you that So you calculate for all components in there. You calculate that all components there.
Yeah, I expand this.
Yeah,
I expand into these 4 terms here.
Yeah.
So now these two again, like I'm not too interested because it does not depend on y. Depend on x. Then let me put outside. So then it's still like proportional to like just the last 3 terms, like proportional to exponential.
So you want to integrate again with x?
No, I don't need to integrate. I just want to look at what's that form looks like.
Oh, okay.
Right. So I can do the computing square trick again, right? I try to computing square for these 3 terms here, right? Trying to make something looks like it looks like it'll be something like what? Lambda xx times something, right? Times something. Should be equal to this guy.
Make it like something like that again.
Yes. So I have like x tilde. Let's see. I put x tilde here. It looks like if I have x tilde multiplied by this is transpose here. So x tilde transpose. Okay, I want to cover this term here. X tilde transpose. If I multiply lambda xx inverse and then lambda xy and then y tilde, then we cover this term, right? Yeah. So hopefully if I repeat this, it should be correct. So lambda x inverse lambda xy. What?
Why from that? So what is the x in there?
What? This which x? This x or this x?
Yeah, this x, yeah. X on there, yeah, that's right.
So check this again. Let's see. This multiplied this by this, I have this term here.
Yes.
And this multiplied by this one, I have this term, I think. And supposingly this multiplied by this, I should get this one. Yeah, it should. Yeah. So if this one transpose is y tilde transpose, lambda xy transpose is lambda yx, lambda xx inverse transpose is just lambda xx inverse lambda xx, x next tilde. So cancel is exactly this guy here. So I have one more terms left. I don't care because the term left is just in y instead of x. That one is constant. Again, I can actually pull it out.
Does not depend on x.
Does not depend on x. But then you see now, okay, I have a format. Like originally, I said this is not done here because this is not a Gaussian format, but this one is. So this one is saying like what is it? This is a Gaussian distribution with mean is basically equal to let's see. I think
it should be cracks again. Mu. Mean is mu also.
Oh yes, I said. X tilde is, by the way, x tilde is equal to x minus mu x.
Yeah.
This is x minus mu x. So therefore, like the mean here should be like mu x minus lambda xx inverse lambda xy y tilde, and the variance is like sigma lambda xx inverse. That's the variance, new variance. And actually, like we by the way, like
so if we divide that, become x and y, so that will be new variance and new means for x.
Yes, we have a new mean and new variance. Let's do not stop here first because it's in lambda. Let's try to make it depends on x sigma. So let's see. By the way, like I have sigma xx, sigma xy, sigma yx, sigma yy multiplied by lambda xx, lambda x, lambda xy, lambda yx, lambda yy is equal to identity, right? because it's inverse one to another. So we used this trick before. And so therefore, let's see. I have let's see, I have sigma xy. I want sigma xy. Sigma xy is here. I want sigma xy and lambda xy. Lambda xy is here. Okay. This multiplied by this plus this multiplied by this. I mean sigma xx times lambda xy. This mode and plus sigma xy times lambda yy should be equal to 0, right?
This is where it comes from.
This row multiplied by this column.
So what you want to prove in there? For this one.
Oh, I want to see like if I can find some expression to replace this in terms of sigma instead.
Okay.
So, and I think I can. Let's see, like because this is equal to 0, then
why it should be 1? Why it should be 1?
what?
Why it should be 1?
No, this multiplied by this it should be 1, but this one should be 0, right?
This one.
Of course. Oh, because this one is the inverse of this guy, right? This is lambda,
Oh, yeah.
this sigma.
Oh, yeah, that's
Yeah.
right.
So and let's see, what's this now? So I can multiply sigma x6 lambda x6. Actually I need something different. I'm sorry. I probably need,
Something different?
yeah, I need this instead. Lambda xx, lambda xy,
Okay.
lambda yx, lambda yy multiplied by this is equal to then the same thing. But like if I do that instead, like I will have like lambda xx sigma xy plus lambda xy sigma yy is equal to 0. And from that I can say I can multiply lambda xx inverse on both sides. So
From where you will find this one?
oh, okay, it's basically doing the same thing, but I flip this to the order of these two matrices. So let me write the whole thing again.
Okay.
So if I have this row multiplied by this column is equal to 0, right?
Yeah.
Yeah,
That's
the
right.
same thing. So
Because you find this one 0.
yeah, it's equal to this, right? Because yeah. So and then I can multiply lambda xx inverse on both sides. So I have like sigma xy plus lambda xx inverse, lambda xy sigma yy is equal to 0. And I can multiply sigma yy inverse on both sides also, like it's equal to sigma xy sigma yy inverse, actually equal to minus lambda xx inverse lambda xy, right?
Hold on. This one actually, yeah, multiplied by this one. So this is down, and this one.
Yeah, and on
so
that
and
one
this one from where?
multiply like inverse of this guy on both.
On both.
Yeah.
Multiply that. Yeah. So.
Sigma yy inverse.
Oh yeah, first.
And then I have like this got cancelled. I can like.
Yeah. So
I also move 3 terms on the other hands. Yeah,
So
I have
you
minus.
just this one and this one. Oh yeah.
Yeah.
And then you minus that. Okay.
Yeah. So but then you compare this. Like this is the same. This guy here. Right? So another way to writing this can be like mu x plus sigma xy sigma xx inverse. Sorry, sigma yy inverse. Y tilde or like y minus mu y, let's say, right? Y tilde is y minus mu y.
Yeah.
And then lambda xx, actually we showed that a couple of times. Lambda xx inverse is actually sigma xx minus sigma minus sigma xy, sigma y inverse, sigma yx. Okay, this is the form, I think like,
you already have this one. Lambda x inverse is like this
yeah, we have that earlier.
earlier.
I think we show, where's that? I'm trying to look for it now. Oh, maybe I already erased that. Let's see. It's somewhere here, right? Yeah.
Yeah.
Remember, like we erased part of that.
Oh yeah.
Yes.
Yeah, that's right. Yeah. That's you substitute with that.
Yes.
So you can scroll down again, and then.
So this is like kind of the final result. So if you make an observation for y, then you have a new variance is like this, and the new mean will be like this. So look at it. This is kind of interesting to interpret. So basically, if you make the observation is just the mean, then it doesn't change your new estimate of your x. So for example, you think of you're trying to estimate your x, then the best estimate will be simply the mean, right? So now if I make an observation of y, that y is kind of related to x, and if my observation is actually the average, is the mean y is equal to mu y, then I doesn't need to change my estimate for x. If my observation is kind of different from the mean of y, then I need to make some adjustment. The adjustment should be like I need to first you can think of this as normalize your y vector, because it's taking the inverse of the covariance matrix, right? And then this is kind of like relating y and x into the x base more or less, and then you make the adjustment. And also there's several interesting things you can interpret here. For example, if x and y are unrelated, uncorrelated, then this will be equal to 0, right?
Uncorrelated.
Sigma xy will be equal to 0.
Why?
So, because I remember when we have something so correlated, I have expectation x y is equal to expectation x times expectation y.
Yes.
This is things that are correlated. And let's see, how do I show that? And okay, and then what is what is sigma xy? Sigma xy is basically expectation x minus mu x, y minus mu y. Let's see, let me make sure I can't make sense here. I think this has I need to put a transpose here, something like that. And okay, I make it complicated. Let's just look at a special case, like xy a scalar. So don't make it too complicated. Let's look at this. It's scalar, so I don't need to transpose. So I have expectation xy, right, minus expectation mu xy, expectation x mu y, and minus expectation mu x mu y. And of course, mu x mu y is just constant, right? It's a constant.
Mu x mu y.
It's the mean of the
What is that?
Here mu x mu y.
Mu x. No,
Mu x and mu y are just constant. So expectation of that is just mu x mu y. And also mu x is a constant, I can pull it out, so it will be like expectation of y, right? It will be like mu x. This term will be the time expectation of y, and this will be mu y as well, right?
Yeah.
So basically, I have this would be plus. So I have minus mu x mu y minus mu x mu y plus mu x mu y. I have minus mu x mu y, right? then expectation xy, right? So if I have things that are uncorrelated, then this will be just equal to 0, right? Because this is expectation x is expectation y.
Mm.
So therefore, like when you have things that are uncorrelated,
Mm.
these two variables, this sigma xy should be equal to 0.
Yeah.
Yeah.
If that's correlate.
And that makes sense, right? Because if it's uncorrelated, then actually another things we can look at, like
But y is actually come from x, so
Mhm.
it's not make sense if not uncorrelated.
what?
Y is come from x, x and y is actually come from one.
Yes, but
and
in general you can
minus
have
one.
them, but you can have those matrices. You can have equal to 0, right?
Yeah.
It doesn't. Of course, in general, it doesn't need to be 0,
Yeah.
but it can happen that they are 0, right?
Yeah.
If this is
That's
equal to
right.
0, then
Yeah.
then that would be uncorrelated, right?
Yeah. So that can be any for y.
Yeah, it can be anything, but then when it's uncorrelated, then okay, actually over time. But if it's uncorrelated, then this will be gone, right?
Yeah.
That's the thing. Then basically, like your no matter what observation you have,
Observation.
yeah, the PDF for y given basically your, if this is equal to 0,
Yeah.
this is basically like p.
PDF in y.
Yeah,
PDF
p is
x.
given y, right?
Yeah, p is given y.
Something like that, right? Something like that, right? So if this is equal to 0, basically this does not depend on, this will be just equal to px, something like that, right? Because it'll be just equal to, or like, let me wait, it'll be just equal to mu x and sigma xx, right? It does not depend on, because this will be gone, right? Sigma xy equal to 0, this will be gone, and this will be equal to 0, like this is gone as well. It's just equal to this guy here.
Yeah, that's right.
So
Something like that.
that means that no matter what you observe, the PDF of x is the same. So what does that mean? It means that like x and y will be independent, right?
Yeah.
So that's actually a proof of like why for Gaussian distribution, when you have variables are uncorrelated, then they will be independent as well. Yeah.
But that is in the independent case. But if y is not independent, it should be like that.
Yeah. Of course, like if sigma xy is not equal to 0, this is the general case, right? The general is maybe like that. But and also you can observe like also this part, like the covariance. Look at that covariance is kind of like become smaller. Actually, this is what you expect, right? When you observe something like your sigma xx, of course, this is hand waving. Like I cannot say smaller is a matrix, but if it's actually, if you look at the what's that, the maybe I can define the trace of the matrix or something like that. That will getting smaller, and that basically is saying that like the variable is becoming more certain.
More centered. Yeah.
More certain, like because the
Yeah,
coherence
because
matrix are getting smaller now.
Yeah, variance is smaller.
Yeah, and that's what you expect, right? Because you make some observation, you are more certain with something now. So now the coherence matrix gets smaller. Yeah.
So it means that if we has a lot of correlation between x and y, so it will be certain.
If you have a lot of correlation of x and y, yeah, it's likely you will decrease more,
Yeah.
and will be more certain. Like if this is size small, then also like the decrease will be of this covariance matrix will be smaller. Again, I will be very careful. Like I will mean the trace of the coherence matrix, something like the decrease will be smaller. Then yeah, then it will be, the change of certainty will not be as much. Yeah. So yeah, there's a lot that you can observe from this one. This is actually pretty cool because for the marginal distribution, it's more like you expect that's reasonable. Like although the proof is tedious, you can guess what is the result right at the beginning. Right, it's a normal and with the same variance. But this one you need to go through the math to know what is exactly the form like. Right?
Yeah.
And this actually gives you some actual result when you do an estimation. When you have a part of the variables you get estimate observed, then what will be the remaining variable like will behave. Yeah.
And then what the application of this?
I guess I'm super over time. I guess I'll talk about it next time. And then after the quiz. Yeah. Okay, I guess I'll stop here. Huh?
Just a clue, the application.
No, I mean also if you have a joint Gaussian distribution somehow, as I said, like then if you observe part of the variables, then you can do estimate of the rest, right? For example, you have those so-called like Gaussian process. For example, you can actually even like financial, you can have like financial data from a Gaussian process kind of distribution. Then you have financial data, you have like part of it observed. For the observed data, you have like with decrease. Actually, I don't have a nice visualization here, but what people sometimes do is like when you have like, so the original distribution, this is like the fluctuation. This is like drawing. Okay, this is a time 1D data, and this is a visualize the, for example, financial data, and this is the mean, let's say, and this is the variance at each time. And then like, let's say if I make some observation here, then like I will affect the other. If I assume the whole thing is a joint Gaussian, I make an observation here, I will change the distribution of the rest of the data. That will look like that. So I basically will have the variance chain like this, then more something like that. So then you can do the prediction. For example, like okay, I make an observation like exactly here. Maybe observation is like that, right? So I'll change the distribution become something like that. For example.
Then is this distribution? This is
let me write it like that.
Variance, not the distribution.
Let me write it like that. So for example, I make an observation like here. Now my new distribution may become like this.
This distribution, new distribution. Oh
yeah. It shouldn't be going more than that. I need to okay. Let's draw like this. For example, like this. So, and then like your estimate will change, right? Your original estimate, for example, here, you estimate here, but instead you move to here, something like. And your variance will change also. So this is like cool. It's not just the estimation will change. Your certainty of your estimation will change as well. Like how certain like something is like you make different kind of certainty of what you observe. Yeah, and you have more observation. For example, if I have another observation here, then I will have something most likely become how to draw it. Maybe become like this. And as you have more and more observation, like you just become more and more precise, like for entire
time series.
Yeah.
So it means that we can find, we can predict.
Yeah, you can predict the future also. Like you look at this also predict the future. Right? Yeah.
That's cool. Yeah, this application. But this is actually the distribution. This one is distribution and this one is variance.
Actually, this should be visualized this way because I cannot how it's very difficult to kind of write it because it's basically you think of this as a time series. For example, I have like a 1,000 samples here, so then it will be 1,000. The n will be 1,000, right? So it's a joint Gaussian distribution with the sigma will be 1,000 by 1,000, right? Something like that. And then maybe you observe like one point here, like this point here. Then the rest will change, right? The mean and the variance for the rest of the variable will change, right? So the original, like at the beginning, the mean for here, like it says like this one here.
This one.
But after two observations, now your mean goes to
another.
goes to for example here now.
Yeah. That's right.
And also like your
Variance alone.
variance also you shrink a lot, right? Variance you shrink from at the beginning is like here, then you shrink to like just this one here.
That's right. That's, yeah.
Is that called a Gaussian process?
Yeah, this is the Gaussian process. Yes.
This give motivation.
Yeah, motivation. Yeah, motivation. I don't know. People didn't start with that. They play with the math, and then after a long while, I don't think they have start with the motivation. They start with the whatever math problem they can solve, and then they.
Yeah, that's
Yeah.
yeah. We can
Yeah.
try it.
Yeah. So I guess we really stop here. So you come back after the test.